2017, higher level, paper 1, question 4. The amount of substance remaining in solution reduces exponentially over time. An experiment measures the percentage of the substance remaining in the solution. The percentage is measured at the same time each day. The data is collected over the first 4 days are given below the table. Based on the data on the table, estimate in which the first day in which the percentage of substance would be less than 0.01%. So it's reducing exponentially. It's not obviously an arithmetic sequence. So what would we mean by exponentially? Exponentially would like 2 to the power of x would be an example of an exponential function. So like if x was 4, then it'd be 2 by 2 by 2 by 2. So you're always multiplying by the same number every time, essentially a geometric sequence. So first thing we do, let's check what OR is. So we know OR will take one term divided by the other. So 42.75 divided by 95, or is equal to, so R is equal to 9 over 20, which is sure, we'll double check it for the crack. We'll take the third one, 9.2375, and divided by 42.75. Yeah, we do indeed get 9 over 20. So it's geometric sequence, and every single time it's being multiplied by 9 over 20. So R is equal to 9 over 20. So multiply 9 over 20, multiply 9 over 20, multiply 9 over 20. Okay, so let's go look at our sequence and series section of our formula book and write down the formulas. So the geometric sequence formula is located in the second section of page 22. And we got Tn is equal to A multiplied by R to the power of n minus 1. So Tn, the term, is equal to A multiplied by R to the power of n minus 1. Okay, so we want the solution to be less than 0.01, and we can see it's reducing every single time. So why don't we find the day that it's equal to 0.01? So Tn is equal to A, which is the first term, 95, or which is the common ratio, 9 over 20, to the power of n minus 1, which is what I don't know. But I know what I do know what I need that term to be equal to. I need that to be equal to 0.01. So first thing, the 95 comes over, it's going to divide. That's going to be 9 over 20 to the power of n minus 1. Now, if what I'm looking for is up here, get the log of both sides. So the log of 0.01 over 95 is equal to the log of 9 over 20 to the power of n minus 1. Of course, using logs allows us to bring the powers down in front. So the log of 0.01 over 95 is equal to n minus 1 multiplied by the log of 9 over 20. 9 over 20 is multiplying that bracket, so when it comes over it divides. So the log of 0.01 over 95 divided by the log of 9 over 20 is equal to n minus 1. And I just want n on its own, so I'm going to take my minus 1 over, and it'll become plus 1. So I have the log of 0.01 over 95 divided by the log of 9 over 20. And the minus 1 comes over to become my plus 1. And that should give me my value for n, the day that is equal to 0.01%. So on the 11.47th day, it'll be equal to 0.01, but obviously we're looking for less than 0.01, and it's not 11.74 or 47, so it'll have to be the 12th day. Part B, a square has a side of length 2 centimeters. The midpoints of the side are joined to form another square. This process is continued. The first 3 squares in the process are shown below. Find the sum of the perimeters of the squares in this process is continued indefinitely. Give your answer in the form of A plus B root C. So we want the sum of the perimeters if this goes on forever. So let's find the sequence that's here. So obviously that's 2 centimeters. And on the inside here, we've got this other square. Okay, so the first perimeter is nice and easy to find. So it's 2, 2, and 2. So perimeter 1 perimeters. Let's say the first one is 8. So what's the next perimeter going to be? So obviously I've got my one outlined in purple here, but if we just focus on this green right angle square here, we know that this is 1 and this is 1, so we can use Pythagoras' theorem to help us out here. 1, 1, and we're looking for this side here. So the side we're looking for, the hypotenuse squared is equal to 1 squared plus 1 squared. So the hypotenuse is equal to the square root of 2. So that's going to be equal to root 2. So I have root 2, root 2, root 2, and root 2. So my second perimeter will be 4 root 2's. Okay, let's find the third one just for the crack. So let's just clean that up. Now I want to find the green square, so if I find the length of one of the sides of this one here, so now the full length is root 2, so half of that is root 2 over 2. Root 2 over 2. So we have another right angle triangle, so again we'll use our Pythagoras' theorem. So right angle triangle, I got root 2 over 2, root 2 over 2, and I want to find my hypotenuse. Hypotenuse squared is equal to root 2 over 2 to be squared plus root 2 over 2 to be squared. So the hypotenuse is equal to 2, and squaring that, that'll give you 2 over 4 plus 2 over 4, which will equal a half plus a half, which is 1, so square root of 1, so h is equal to 1. So we get 1, 1, 1, 1. So the perimeter of the fourth square then is 4. So there's some sort of sequence going on here. Let's check if it's an geometric sequence. So we check that by doing 4 root 2 divided by 8. Let's just check if that's the same as 4 divided by 4 root 2. Yeah, they are the same, so it's a geometric sequence, and we've just established that the common ratio here is root 2 over 2. So I want to find the sum of the perimeters, so the sum means we're using some sort of S formula. So we check our formula book for, and it's going on indefinitely, which means it's going on forever, so we're going to check for the S infinity formula. Page 22, the sum of an infinite geometric series is A over 1 minus R. So S infinity equals A over 1 minus R. So S infinity in this case, A is the first term in the sequence, 8 over 1 minus an R we've established is root 2 over 2. We'll calculate that then to get our S infinity. And we get 16 plus 8 root 2, which is what they're looking for here, and it's centimeters.